this video, we're going to prove the following fact. For any integer 1 or above, for any positive integer, tau of n must be less than 2 times the square root of n. But first we need to get this silly lemma out of the way. It says positive divisors of n almost always occur in pairs. Okay, let us first do the proof of the lemma. And talking about proofs, if you like seeing mathematical proofs, then you should certainly subscribe to my channel, as that's all we do here. Suppose D1 and D2 are both divisors of n such that D1 times D2 is equal to n. Can both D1 and D2 be less than the square root of n? Let's see. D1 is less than the square root of n, and D2 is less than the square root of n. That implies D1 times D2 is less than the square root of n times the square root of n, which is n. So no. If D1 and D2 are both less than the square root of n, they have no prayer of multiplying out to n. What if they're both? So the answer is no. The answer to my question is no. Now, can they both be bigger than the square root of n? Can both, and I should say the following. I should say this following, where D1 and D2 are different. Can both D1 and D2 be greater than the square root of n? Again, where D1 is not equal to D2, and where I said D1 times D2 equals n. Well, if D1 is bigger than the square root of n, and D2 is bigger than the square root of n, then if you divide the two numbers that are bigger than the square root of n, their product will be bigger than the square root of n times the square root of n, which is n. So D1, D2 is strictly bigger than n. So we conclude the following. We conclude that if D1 times D2 equals n, then D1 is bigger than the square root of n, or definitely not or. I was thinking of something else. And D2 is less than the square root of n, or I have them in reverse. D1 can be less than the square root of n, and D2 can be greater than the square root of n. There's no way about it. If you take two numbers that multiply out to n and they're not both the same numbers, then one is less than the square root of n and one is more than the square root of n. That is, they come in pairs. Okay, D1 and D2. Okay, so, okay. Yeah, I've already said d1 times d2 equals n. So either one is less than square root of n and one is bigger than the square root of n. That's what I mean by pairs. Okay, so let's see. If, let's just use a different letter. If b is a divisor of n, then n over b is another divisor of n. And b is not the square root of n. Because if b were the square root of n, then you'd have n divided by b, which is the square root of n. I don't want these numbers to be the same. So, divisors of n come in pairs. So, divisors of n come in pairs if one divisor is less than the square root of n, or bigger than the square root of n. So what is this? Almost always come in pairs. If c is equal, okay, so let's say it this way. If n is a perfect square, then n equals to m squared, and m times n equals m. That is, m is a divisor that has no pair. That has no pair. Okay? It's itself. Alright. So, if n is not a perfect square, then divisors come in, all divisors come in pairs. In fact, whether n is a perfect square or not, all divisors less than the square root of n will have a match where the other divisor multiplies out to n and is bigger than the square, it's bigger than the square root of n. And I kind of have that right here. No matter what b is, as long as it's not the square root of n over b will not be the square root of n. And one of these numbers is bigger than the square root of n, and the other one is less than the square root of n. Okay, so let's get this out of the way. You probably already knew this, but for completeness, I felt I needed to put it down. So now we want to show that for any integer, any positive integer, tau of n is less than or equal to 2 times the square root of n. Now, I'm going to do this proof in 2 cases. Case 1 is n is not a perfect square. N is not a perfect square. Let m be less than, well, it can equal. Let m be less than the square root of n, such that m is the largest possible integer. In other words, if you have the square root of 17, the largest integer that's less than the square root of 17 is 4. Because the first number below 17 that I know the square root of is 16. And the square root of 16 is 4. The square root of 17 is less than 5, which is the square root of 25. The square root of 17 is less than the square root of 25 because 17 is less than 25. If you look at the square root function, it is strictly increasing. That is, if you have a and b, and a is less than b because it's to the left, then the square root of a is going to be less than the square root of b. So that's how I defined m. If n was 17, then I would let m be 4. That is, if I go to 5, it won't be less than the square root of 17. Now, there are exactly m numbers from m all the way down to 1. The possible values, now did I say that, okay. The possible divisors of n, which are less than the square root of n, are 1 and 2 and 3 all the way up to m. Those are the possible divisors. If I give you the square root of 32, which is less than 5, and I say, what are the possible divisors of 32 that are less than 32? Well, you should try 1, 2, 3, 4, or 5. I'm asking you to find divisors less than the square root of 32. You know, there's no point in trying 6, because that's not what I'm asking for. 6 may divide 32. I'm not saying no. I want the numbers less than the square root of 32. I would only try those 5. Okay. As a result, okay, wait. Let me just say that there are m of them. So, there are at most m divisors of n which are less than the square root of n. But by that lemma, there exist at most m divisors of n which are greater than the square root of n. Okay, by the lemma, there exist at most m divisors of n which are greater than n, the square root of n. Putting this together, there's at most 2m. Putting this together, there are at most 2m divisors of n. So we know that tau of n is at least, well, is no bigger than 2m. Now, we also know that so far this side and this side are equal. They both have 2. But instead of m, I'm going to put something bigger than m, the square root of n. Okay, how did we get m? It was the largest number less than the square root of n. Recall, m is less than the square root of n. So, we have it. T of n, actually, this is strictly less than. T of n is less than 2 square root of n. But this was in a special case. This is in case 1 where n is not a perfect square. Now, we can go on to case 2. N is a perfect square. Suppose that n is equal to m squared. Now remember, there are half the numbers, as many divisors of n that are less than the square root of n. This implies the square root of n is m. As many divisors of n that are less than m, there are just as many that are more than m. And there's one more divisor, n itself. Note that m divides m squared. That is, m divides n. That is, m is a divisor of n. Okay. So basically, from case 1, we have at most m minus 1. We have at most m minus 1 divisors of n, which are less than the square root of n, better known as m. We have at most m minus 1 divisors of n that are less than the square root of m, which is m. Remember, in case 1, I wanted the first integer that is less than the square root of n. That is, I want the first integer less than m. That's m minus 1. And likewise, there exists at most m minus 1 divisors that are larger than m. There exists at most m minus 1 divisors of m that are greater than the square root of n, which is m. And m is a divisor. So tau of n is at least m minus 1 below m divisors plus 1, that being m itself, plus the up to m minus 1 divisors that are bigger than the square root of n, which is m. This turns out to be, well, m plus m is 2m, minus 1 plus 1 is 0, minus 1. Now, this here is less than 2m. Nobody's going to argue that. That's less than 2m. But m is the square root of n, which kind of surprised me, because now we got tau of n is less than or equal to this, which equals that. That is, tau of n is less than this, less than or equal to this, but is strictly less than 2m, which happens to equal this. So it's less than 2n, 2 times the square root of n. Combining both cases, we have that tau of n is less than the square root of, less than 2 times the square root of n. We got that result in both cases, therefore it's always true, and I have an error up here. I shouldn't have less than or equal to. Now, since I think where I got the problem from, it said less than or equal to. Let's look at n is equal to 1. So, tau of 1, well, there's only one divisor. And does that equal to, no it doesn't. Does it equal to 2 times the square root of n? Well, that's 2 times 1, which is 2. Tau of 1 is not equal to 2 times the square root of 1. In fact, it is less than. So I am going to modify this and say that t of n, tau of n, is strictly less than 2 times square root of n. If one of you sees an error in my proof where it should say equal, or it must say equal, then please leave that in the comment. Now, just for the record, I can leave equal, okay? Because if tau of n is less than 2 times square root of n, that does imply that tau of n is less than or equal to, less than or equal to 2 times the square root of n. It does imply that. The implication does not go the other way. So you can leave the less than equal, but let's do a stronger. Let's state the theorem stronger. It's strictly less than. Okay, so I satisfied my doubt, and it should be less than, in my opinion. Once again, if you think otherwise, please tell me where you think that's needed. If you like watching math videos like this, subscribe to my channel. See you guys in the next video. Don't forget, watch and learn.